Hello and welcome to this presentation titled Understanding the Effect of Alkalis on IDR and DR zones in blast furnace. In this session, we will explore how the presence of alkali like potassium oxide and sodium oxide can significantly alter the internal reaction zones of blast furnace. This topic is very crucial because even a teeny, or we can say even a stress level of alkali can affect reduction mechanism, co-reactivity, and ultimately the furnace energy efficiency, which all mix up to reduce the productivity up to a very low level. And the sensitivity, the rule of thumb to also direct towards the impact of alkali, as we know that each kg could able to drastically increase our coke rate around 5 to 6 kg. So it's a huge value. Now coming to the next slide, which gives us a basic background of the key reaction zones in blast furnace and the type of reduction occurring in each. In order to find the consequences of alkali over direct reduction and indirect reduction, this slide is going to be a foundation stone. As in the top row, it has already signified that 400 to 800 degrees Celsius, we see progressive reduction of iron oxide, that is Fe2O3 to Fe3O4 and finally to FeO. Now, this is entirely done by carbon monoxide as we know, and it's known as indirect reduction. Now comes a other zone, that is TRZ or thermal reserve zone, which typically span 950 to 1050. Here FeO is reduced to metallic iron, steel through CO gas, making this zone a part of indirect reduction regime. So entire this zone is occupied by indirect reduction zone. And finally, in the lower shaft and wash, where temperature exceed that is more than 1050 degrees centigrade, then FeO is reduced to iron directly by solid carbon, which defines the direct reduction zone. Now, understanding this zone is essential before we look at how alkalis shift these boundaries inside the furnace. Because as the boundary shift from upper or lower, then the length of one zone increases, another zone decreases. Now coming to this slide where it shows uh, our with presence of alkali or increase in alkali actually increases the rate of reaction of gasification or Boudouard or solution loss. A lot of name is there. So here we can say that with the alkali or Boudouard reaction start occurring early. So this is one of the very significant phenomena occurring in presence of alkali. And this slide highlight how alkali interfere with the thermal and chemical profile of blast furnace. In normal condition, the Boudouard reaction where carbon react with carbon dioxide to form carbon monoxide becomes significant around 1000 degree Celsius. But in the presence of alkalis like potassium and sodium oxide, this reaction begins earlier at approximately 900 degrees Celsius. Now, what happens? This premature reaction consume energy within the thermal reserve zone. These occur at the cost of, we can say, thermal reserve zone or TRZ, and by doing this, reducing its temperature. As a result, the indirect reduction becomes incomplete at higher level, meaning Fe is not fully reduced by CO. So I think we got the point. So Fe is not fully reduced by CO before reaching the lower part of the furnace. So these unreduced FeO now enter the lower zone, forcing the direct reduction zone to extend upward to complete the job. And this change alter the internal dynamics of the furnace and affect the efficiency, which we will explore in the next slide. Now let us take a simple calculation for our better understanding is using a 30-meter tall blast furnace. Now where we assume the normal thermal reserve zone has a height of around 1.5 meter. Now, in this case, we have taken two cases, case A and case B, and we'll try to compare and see the how we have learned from this case A and B. Now, case A, which is the normal condition without alkali, shows a typical profile, the IDR profile or IDR zone, we can say, where indirect reduction occur, is around 8 meter tall. The thermal reserve zone site as a 1.5 meter isothermal plateau centered near 1000 degrees Celsius. Now, if we talk about a direct reduction zone, it lies at the bottom and about 1.5 meter in height. Now, let's compare that with case B, where alkali are present. Due to early coke gasification, the thermal reserve zone shift downward by about 100 degrees centigrade. Their height is reduced to zero point 0.8. That is what we have. Again, I want to repeat that the by coke gasification temperature down by 100 degrees centigrade, and that result into height reduced by zero point 0.8 meter. Now this causes the IDR zone to shrink correspondingly, now measuring just 6.5 meter. As more FeO enter the lower part of the furnace unreduced, the direct reduction zone must compensate and its height increases around 3 meter. So we can say that now it cost a penalty of coke. This example shows how even a modest chemical change like the presence of alkali can significantly shift the reaction zones inside the furnace. As in this slide, we try to have a quantitative comparison of the zone's height. This also summarizes the quantitative change in the zone height within blast furnace due to alkali presence. Without alkali, the indirect reduction zone has a height of 8 meter. With the alkali, it sinks to 6.5 meter, showing a reduction of 1.5 meter. The thermal reserve zone also compresses. It dropped from 1.5 meter to just zero point 0.8 meter, a decrease of 0.7 meter. On the other hand, the direct reduction zone expand significantly. It double in height from 1.5 to 3 meter, a net increase of 1.5 meter. So these changes clearly reflect how the internal balance of reduction mechanism shift due to alkali driven early coke gasification. Now such shift not only impact reaction efficiency, it is not going to have a only reaction efficiency change, but also affect overall fuel consumption and furnace stability. So now we will discuss the most important part is the consequences of IDR to DR shift. So this slide summarizes the key operational consequences when the reduction mechanism inside blast furnace shift from indirect reduction zone to direct reduction due to alkalis presence. So let us go through each aspect. Coke rate increases because as you know, uh, as the direct reduction increases, coke rate is to be increased because due to its more heat taking effect, gasification heat taking effect, we must have to compensate, otherwise furnace will go out of our control. So coke rate increases because direct reduction uses more solid carbon compared to indirect reduction, which rely on carbon monoxide gas, and then gas efficiency drop because since less carbon monoxide is reused in the indirect reduction, so that is also a big reason for drop in gas efficiency. Heat requirement also increases as direct reduction is more endothermic, demanding more energy. Productivity may fall because the reduction slowed down in direct reduction compared to the faster indirect route. Slag volume may also increase, especially due to excess ash coming from the higher coke consumption, which is quite obvious due to drop in gas efficiency and increase in coke rate. Lastly, tapping temperature may also fall as more heat is absorbed in endothermic reaction, requiring careful operational adjustment. And this is visible, this coldness is visible during the furnace day-to-day normal trends, where we can see that stock line have a different type of profile where it shows there is a slip, and at the same time there is a variation in the DP also, in understanding that this slip is the reason for this coldness. Coldness is the reason of this sleep. So now coming to the next part of our slide, which is a summary slide, we can wrap up with the key takeaways from this presentation. And out of so many learning, the first is about the alkali, which catalyzes the Boudouard reaction at lower temperature, which leads to early coke gasification. And this gasification totally crumbled the coke original structure. So this disrupt the normal thermal balance inside the furnace. As a result, heat is robbed from the thermal reserve zone, or TRZ we can say, which reduces the effectiveness of indirect reduction. Consequently, the IDR zone shrink by approximately 1.5 meter, and direct reduction zone increases to handle to extra FEO feed load. This is as per of our understanding with respect to our example shown. Now, these shifts make the blast furnace operate less efficiency. That is well understood by the whole presentation. The operational penalties are serious: increased fuel cost, higher refractory wear, and a drop in overall productivity. So, managing alkali input and monitoring their impact on reaction zone is therefore crucial for maintaining furnace health and efficiency.